So welcome everybody to the webinar of today. The speaker of today is Edoardo Rosti, and he's going to talk about polymeric turbulence. So as usual, I introduce the speaker very briefly, and then I leave him the floor. So Edoardo Rosti is an assistant professor at the Okinawa Institute of Science and Technology in Japan since 2020. He received a Master in Aeronautical Engineering from Polytechnic of Milano in 2013 and a PhD in Aeronautical Engineering at City University of London in 2016. Before joining OIST, he spent time as postdoctoral fellow at the KTH Royal Institute of Technology in Sweden and at the University of Tokyo in Japan. Marco's research interests are in the general area of multiphase turbulence, complex fluids. He was the recipient of the Human Award for Distinguished Young Researcher in Fluid Mechanics by the Japanese Society of Fluid Mechanics in 2021, and is Associate Editor of the European Journal of Mechanics B and Editor of Results in Engineering. So it's with great pleasure that I introduced Marco Edoardo Rosti for the talk of today. So I will now stop sharing my screen. Marco, if you want, you can start sharing yours.
Perfect. Thank you very much for your kind introduction. So now you should be able to see the screen.
Yeah, perfect.
Okay. So first of all, thank you everyone for joining today. I know that usually you have this kind of seminar at a different time, but here in Japan, it's already quite late. So thank you for the change of your schedule. So as Francesco said, so I'm Marco Rosti. I'm at the Okinawa Institute of Science and Technology. So for those of you who don't know it, so we are a new university. So we are located in Okinawa, which is this small dot in the south of Japan. Okinawa is a quite nice place to live. It's surrounded by a coral barrier. And this is OIST, so it's a graduate university. It was founded 10 years. Well, it became a graduate university 10 years ago, and it was founded 20 years ago. Here, I have I'm leading my unit. My unit is called Complex Fluids and Flows, and these are the members. So in this period, actually, OIST is hiring for new faculty position, mostly at the tenure track level, but also for more senior professors. So if you're interested, feel free to contact me. So today's talk is about polymeric turbulence, and I divided the talk in two parts. The first one is this one, so polymeric turbulence at large Reynolds numbers. And this work was done in collaboration with Prasad Perlakar and Victor Balditia-Mitre. In the second part of the talk, instead, I will speak still of polymeric turbulence, but this time at low Reynolds number. So let's start with this. So why we started studying turbulence, polymeric turbulence? So this is a quite broad topic that has interested many researchers, especially since it was discovered that small amounts of long chain polymers dispersed in a turbulent flow, mostly in pipes or channel, can produce large amounts of lead reduction. So this has triggered the interest of researchers who try to understand how this was achieved, and in order to improve even more the control of the flow. So once we add the polymer to the flow, we have at least an additional obvious, let's say, non-dimensional number that is the polymer concentration, so how many polymers we're dispersing in our flow. But apart from that, there are two fundamental non-dimensional numbers that will control the kind of flow that we are looking at. The Reynolds number, so the usual one, so the ratio between the inertial and the viscous terms, the Navier-Stokes. And the addition of polymers introduce a new one, which is maybe less famous, which is called the Deborah number. So the Deborah number is simply a ratio of two timescales, one of the polymers and one of the flow. For the polymer, the typical timescale that is chosen is the relaxation time of the polymers. While for the flow, so since we are speaking of turbulent flow, we have a large number of timescales that we could choose. So in the past, usually it was common to choose the Kolmogorov timescale, so the timescale corresponding to the small scale of the flow. But instead here, I will use the large scale, so the time scale of the large scales, and later I will show you why I made this choice. So we have these two-dimensional numbers and the polymer concentration, which instead we will keep it fixed. So once we add the polymers into a fluid, so there is an elementary effect of it, which is increasing the viscosity of the solution. Notwithstanding this is the resulting dissipation, turbulent dissipation of kinetic energy can actually be reduced. And the reason for that is that the polymers, apart from changing the viscosity of the overall of the mixture, actually are able to alter the turbulent cascade not only quantitatively but even qualitatively. To understand this, as I said, a lot of work has been done in the past. So what is sort of established now is that there is a specific an intermediate length scale, LP, I call it LP here, which is intermediate between the largest scale of your flow, so L injection, which could be, for example, the scale at which we are injecting energy to the system, and LK, which is the smallest length scale of the flow, so usually called Kolmogorov length scale. So LP is an intermediate scale between L injection and LK. And what it was found in the past is that for scales larger than this LP, so between LP and L injection, so the energy spectra was decaying similar to in Newtonian fluid, so we will carry the wave number to the power of -5/3. And by consequence, the second order structure function was growing with R to the power of 2/3. So this was for L larger than, for R, for scales larger than this intermediate scale LP. For smaller scales, instead, the energy was then is where, let's say, the other scales where polymers are actually altering the energy spectrum. And in particular, usually it was found that the energy spectrum was steeper than the usual typical Kolmogorov spectrum. So this has been found by a lot of work. So in this plot here, I'm showing the Reynolds number of some simulation that we took from the literature versus the Weisenberg numbers. The Weisenberg number, it's rough. You can it's a different way of measuring the measuring, let's say, the elasticity of the polymer. So it's not the Deborah number, but you can sort of, let's say, they are roughly proportional. So you can see that most of the polymeric flows that were studied in the past had the Reynolds number usually below 100, and this Weisenberg number instead was going from very low number, like order 10⁻², up to a value of around 100. So if you rescale this Weisenberg number to have a Deborah number, for my specific case, there is a factor between 100 between the two. So it would mean that this is a Deborah number of 0.1 based on the larger scale of the flow. So this was this is what was done in the past, but a couple of years ago, there was this paper published by Zhang and collaborators, Science Advances, who performed some experiments. And what they found is by increasing the polymer concentration at a very large Reynolds number, what they found is that the structure function were actually not growing in the similar way as the Newtonian flow, so with R to the power 2/3, but they noticed that these structure functions were growing with different exponents based on the amount of polymers that they were adding to the flow. So what we decided to do was to try to see if we were able to capture this phenomenon and try to explain it. To do that, the most important thing was to be at high Reynolds number. So the simulation that I will talk about are over here. So we are at the Reynolds number based on the Taylor-Martin scale, which is order of 400. So it was larger than what was done in the past. There is only one simulation in the past of polymeric turbulence done at this Reynolds, which was done in the past, but the Weisenberg number was still relatively low. So we had to push the Reynolds number to a very large number and as well the Deborah number. So you can see that we, the simulation that I will talk about, have a Weisenberg number ranging from order 10 to 1,000 or more than that, which in terms of Deborah number means that we go from a value of 0.1 225. So all the results that I will talk, at least in the first part, comes from these 6 points over here. So just to repeat, the Reynolds number is fixed to a value of around 400, and the Deborah number will vary between 0.1. It will be 1 in the middle of our range, and it will go up by for the So how I solve this problem? So in my unit here, we do direct numerical simulation. And the specific setup that we chose was homogeneous isotropic turbulence. So we have a 3-periodic cubic box. All sides of the box are periodic. And inside this, we have our non-Newtonian fluid. These are the equations that we solve. So the first two are basically the standard Navier-Stokes equation. There is only one extra term, which is the last one here, which takes into account the non-Newtonian feature of the flow. So this term has the two parameters, mu p and tau p. So mu p is the polymer viscosity. Tau p is the polymer relaxation time, so which is what we use to define our Deborah number. And then we have this C, which is a tensor. It's called conformation tensor. And to find this conformation tensor, we need to solve one additional equation. It's a tensorial equation reported here on the bottom. So all these equations are fully coupled. So in the polymer equation, we have the fluid velocity, and in the fluid velocity, we have the polymer conformation tensor. So this equation actually can represent multiple models. So in this talk, I will mostly show you results for the ultra-ordinary model, which is a very basic, I'm saying, non-Newtonian, purely elastic fluid model. Just for the sake of comparison, in some cases, we actually perform also simulation with the FNP model, but just to verify that the results were not too different depending on the model. So we have this set of equations. To maintain a turbulent state in our 3-periodic box, we need to continuously inject energy into the flow. And we do that with random forcing. In particular, we use the one developed by Edoardo and Pop. And in this case, we decided to inject energy at the largest wave number. So for k equal 1 and 2, we are injecting energy in the flow, and then energy is dissipated at the smaller scale. So our Reynolds number is pretty high, so it's 400. So in order to properly resolve it, we need to discretize our domain with a lot of grid points. So in particular, we have around 1,000 grid points per side of the box. With this, we reach a solution which is a sort of standard for this kind of simulation. Yeah, and all of this was solved with we have a code which developed here in my unit. The name is Fuji, which is the same code that we use for all kind of simulation, and it's been validated for many kind of flow configuration. So this is just the basic setup. So now let's go to the more interesting parts of the results. So these are 3 typical snapshots of the flow that we obtain. So the flow, remember that we are solving a 3-periodic box, so we are 3-dimensional. So this is just a slice passing through the middle of the domain. And starting from the left, so in these plots, I'm showing the contour of the magnitude of the vorticity. So in the left, we have the Newtonian fluid. So you can see the presence of these very small details, region where vorticity is large, and as well the regions where vorticity is very low. And these are, we can have a similar picture if we think the participation, and this would represent also the presence of intermittency. So the left plot is the standard one that you can find it in a large Reynolds number turbulent flow. Then the other 2 plots instead are the same quantity in the same plane, but shown for a polymeric fluid at 2 different Deborah numbers. So in particular, I choose Deborah 1, which we will see will be a special case, and the Deborah 25, which is the largest one that we investigated in this work. So for Deborah 1, you can see that, first of all, these very small scale features of the flow sort of disappear, and they are replaced by this very elongated structure, which spans across the domain. What is interesting and led us to do further work is actually if we increase Deborah even more. So if the fluid becomes even more elastic, thanks to the polymers, we see a sort of return of the small-scale structures that we were seeing in the Newtonian fluid. So it seems that there is a kind of non-monotonic behavior in the flow, happening in the flow, and that's what we will try to investigate quantitatively in the next slide. So to study this flow, what we do is we started looking at the energy spectra. So this is the energy spectra. So E, I will call it E in this slide, in this talk, function of K, the wave number. So small k are the largest scale of the flow. So in particular, this value here on the left is the largest, is the size, is the wave number corresponding to the box size. And then large k instead correspond to the small scale of the flow. So we can see here, this is the results for the lowest Deborah number that we investigated. We can see that we have at the large scales, so at small k, we have a range of scales in which the energy decays as a power law, followed by a faster than a decay. So the range where we have this power law decay is what is usually called inertial range. So in this case, our energy spectra is decaying with a power law, which is exactly -5/3. So in all these plots, in the one that we saw later, a dashed line represents the Kolmogorov scaling, which for the energy spectra is -5/3. So this is sort of what has been studied in the past. You have at the larger scales the typical Kolmogorov flow, and then at the smaller scales you have a decay which is faster than the Kolmogorov scale, than the Kolmogorov scaling. Now the interesting part comes when we start ramping up the value of the elasticity of the polymers. So we go, we double first the Deborah to 0.3 and even more to the value around 1. What we can see is that at the larger scales, the Kolmogorov scaling keeps be present. What is happening is that the range where this the Kolmogorov scaling is holding shrinks. In particular, the right bound of the scaling is moving to the left, and this is replaced by a new scaling, by new power law scaling, which is especially evident for the Deborah around 1, which is indicated by this solid line. And the power law, the exponent, let's say, of this power law decay is 2.3, so -2.3. So what I will call this new scaling elastic scaling range, and we will try to see, let's say, what originates this. Before going to that, in the previous plot, the slice of the vorticity field, we saw that if we increase the Deborah number beyond 1, so we were seeing a return of the small scale structure typical of the Newtonian case. So we further increase the Deborah number also in terms of the energy spectra. And what we see is that when we increase the Deborah number beyond 1, so the Kolmogorov scaling range starts increasing again. And for a value of around 5, let's say, it's minimal. And beyond that, so it's 25, we don't see it anymore. So for the largest Deborah number, we see only, again, the Kolmogorov spectra, same as what we were finding at the low Deborah number. So basically, just to summarize this picture, is that as we increase the Deborah number from low values, the inertial range of scales where the Kolmogorov scaling holds shrinks towards larger scales. A new scaling range appears, which we call elastic scaling range, which has an exponent of -2.3. This elastic scaling range is maximum in extension for Deborah around 1. And if we further increase the Deborah number, this elastic scaling range shrinks and eventually disappears, leaving again only the typical Kolmogorov scale. So this is report what we found. To understand where this comes from, well, before going that, so since we have these two, let's say, scaling range, we can actually define 3 characteristic length scales of our problem, and equivalently, in this case, with numbers. So first of all, we have the injection the largest scale of the flow, which is roughly the integral of length scale, which is let's say the left side of our plot. So the two other length scales of interest are, one is what we call before LP, so the scale at which the Kolmogorov scaling ends, which I indicate here by this circle, and you can see that this scale moves let's say towards largest wave number, towards smallest wave number, so largest scales for Deborah less than 1, and then moves back to largest wave number, so smallest scale for Deborah larger than 1. So this is the second scale, and the third one is instead the scale at which the dissipative range, let's say, starts, which are indicated by this square. So for Deborah 1, for example, you can see that you have the injection scale, which is the largest scale of this plot, followed by this polymeric length scale, and finally followed by the dissipation scale. Okay. So to understand how these scaling range are generated and where they come from, and in particular why we have this non-monotonic behavior, we look at the energy balance. So the energy balance is this equation express how energy is transferred across the scales. So we are considering statistically steady state turbulent flows. So the left hand side, which is the time derivative, the kinetic energy, is 0. So we have that the terms on the right, they sum up to 0. So we have 4 terms for our flow: pi f, which is the terms coming from the nonlinear term of the Navier-Stokes equation; df, which is the terms coming from the viscous diffusion; p, which is the polymeric, the terms coming from the polymeric stress, so the additional term that we have in our momentum equation; and F injection, which is the power due to the forcing that we are injecting on the larger scale. In a typical Newtonian fluid, so P obviously will be 0. So we would have that pi, that F injection is non-zero only at the largest scale, and it's 0 everywhere else. Then it will be so for the largest scale, F injection is dominating. Then for the intermediate scale, pi, so the nonlinear energy flux would transfer energy from the larger scale down to smaller scales, and then finally this energy would be dissipated at the smaller scales by the that dominates. In the case of polymers, we have this extra term, which is the interesting part of this talk. And to understand it, we plot it here. This is the shape of P as a function again of the wave number. And this is for the case of Deborah equal 1, so the case where we have this elastic scaling range, which is which shows the maximum length. So we want to understand its shape. So as I said at the beginning, so an obvious effect of polymers is to increase the viscosity of the flow. So as a consequence, also it has this polymer term acts as a dissipative term. So you can see that it starts from 0 at the largest scale, then grows, and it saturates at the smaller scales. So this is the shape of a dissipative term. However, it's not a purely dissipative term, because you can note that this P is first growing, it reaches a maximum value at intermediate scale, and then slightly grows, decays, reduces again. So to be a purely dissipative term, this would have been purely monotonic. So the fact that it's non-monotonic, so led us to decide to split it into 2 contributions. One, which we call it dP, which is a purely dissipative term, so it's purely monotonically growing. And then the remaining, so the difference between P and dP, we call it pi P, and it looks like another energy flux. So it starts and ends at 0, and it is maximum at intermediate scale. How to define this quantity? So as I said, pi is simply the difference of the other 2. So the difficult part was to decide, say, how to model D, so the polymer dissipation. And we decided to do that by giving it the same shape as the fluid dissipation, just rescaled to provide the correct value dissipation. So this is, of course, an hypothesis. It's not exact. but we tried different options. So we can choose different shapes for the polymer dissipative term, but the overall results don't change. They slightly change quantitatively, but qualitatively, everything that I will say after this slide will not change by the shape of this dp. So we actually are pretty satisfied by this approximation. So for us, this is just a definition. We define this term in this way, and the pi p is just the difference of the average. So let's say a way that support this decomposition is shown here on the right plot. So what I'm showing here are only the nonlinear energy flux, pi, which for the Newtonian case is this black line. And then for the polymeric case, the nonlinear energy flux is this solid red line. So if we sum to the nonlinear energy flux in the polymeric case, this solid line, the polymer flux, pi p, found by using this relation, which are these crosses. So the sum of these two contributions gives this red dashed line, which you can see quite well resembles the nonlinear energy flux given by the in the Newtonian case. This is sort of let's say support how we decompose the polymeric flux, because the energy that we are injecting in the Newtonian case or in the polymeric case is the same. So the energy that needs to transfer down at the same at smaller scales is the same. So the fact that these two lines are quite close, I think is it's a good way to suggest that this decomposition is not bad. Anyway, if we trust this, we can compute these terms for all the cases that we have simulated. And now there are many curves. So this is the energy balance for all the cases. Again, we go from a small Deborah number on the top left. Deborah then increases going towards the right. The red case is the one with Deborah equal 1, and then Deborah larger than 1 is the bottom curve, is the bottom one. So the solid line is the nonlinear energy flux. The line shown with the plus symbol is the polymeric flux. And then we have these two dissipation terms. So the dashed line is the fluid dissipation, while the crosses is the polymer dissipation. So for the low Deborah number, so the polymeric terms, so the two symbol curves, are subdominant at every wave number. So the terms which dominate the energy transfer are actually the nonlinear energy flux and the fluid dissipation. This is why in the energy spectra we were seeing the typical Kolmogorov scaling at the large scales, so where the nonlinear energy flux dominates. And then we were seeing a fast decay of energy where in the dissipative range where dissipation dominates. This let's say configuration is found again at the largest Deborah number, where again the polymeric terms are relatively small, and the dominant contribution comes from the fluid nonlinear energy flux and the fluid dissipation. So the interesting part, so the cases where the polymeric scaling was found are the cases in which one of the polymer terms, actually both of them, are dominating into a certain range of scales. So for example, for Deborah 1, you can see that initially energy is transferred by the nonlinear energy flux. Subsequently, energy is transferred by the polymer energy flux. And finally, energy is dissipated. In particular, for all these cases, energy is actually mainly dissipated by the polymeric dissipation. Now, the range, let's say, in which the nonlinear energy flux is the dominant contribution, which is indicated, let's say, which is bounded by this circle and the square, is actually exactly the range in which we were observing the 2.3 decay of the energy spectra. So this led us to conclude that in the range similar to Newtonian fluid case, in the ranges of scales where the nonlinear energy flux dominates, we find the typical Kolmogorov scaling. In the range of scales where the energy the polymeric flux dominates, we find the elastic scaling, and then after that we will find the typical dissipation. So note that this symbol, which here indicates the intersection between the dominance contribution, are actually exactly in the same wave number where one of the previous plot, which I can go back here, are actually the same wave number that I put here. So this suggests that at least the two results in terms of energy spectra and in terms of energy balance are consistent. So we are able to explain why we see a different energy spectra. So we see a different decay of the energy spectra because there is a different energy flux dominating the energy transfer. However, we are not able to explain why the power law is 2.3. So that's something that's open for the future. So all this was done in the Fourier space. We can actually repeat the analysis in the real space. And to do that, a typical quantity to compute is this one. So this is called the structure function. Basically, what it is, it's the difference between the velocity between 2 points separated by distance r. So I have 2 points, each one with a different velocity. The distance between them is r. I take the difference, I project along the direction of their separation, and then I take a certain power, p, and then I average. So for p equal 2, actually, the second order structure, we have S2, the second order structure function, which can be shown to be, at least in a periodic box, to be exactly the Fourier transform of the energy spectrum. So if you have an energy spectrum which decays with a certain power minus c, we can find it's possible to show that the second order structure function grows. So this should be r, with r to the power of c2, where c2 and xi are simply related by this formula. So in our case, the energy spectra, for example, was decaying with the power of minus 2.3. So here psi is 2.3, 2.3 minus 1 is 1.3, which is how our second order structure function should grow. This is actually what was found in the experimental paper by Zhang et al., the one that I mentioned at the beginning of the talk. So what they were not able to they didn't perform a Fourier analysis. They only look at the structure function in the experimental setup, and what they were finding is that the structure function was growing with this exponent. So our results actually are consistent with the one from the experiment. Okay, so if our energy has this power law, we should expect an S2 going with this exponent. What in our case, actually, we have two scaling ranges. So we have the energy spectra, which in one case, which at the largest scale is following the Kolmogorov spectra. So the energy is decaying with the power minus 5/3, which means that the structure function is growing with the power of 2/3, which is what's indicated here by this dashed line. And then we have the elastic scale, which was at a smaller scale, in which the energy was decaying with the power of minus 2.3, meaning that the structure function is growing with 1.3. And indeed, that's what we found here with this solid line. So that's okay for this 2. If we increase the order, say, of our moments, so we go with P to 4 and 6, for example, now we can go some orders in theory. What we found out is that actually they're not simply the exponent of the structure function is not simply twice or 3 times the one for S2. That's something that happens also in Newtonian turbulence. So it's a footprint, let's say, of intermittency. And the same actually seems to happen here. The interesting thing is that for the Kolmogorov scaling part, so the one that I indicated with the dashed line, so these dashed line are not the original Kolmogorov prediction, but they are the Kolmogorov prediction corrected by the intermittency correction, the one that are typically used in turbulence. And we found out that seems that the same intermittency convection holds also for these polymeric turbulent flows, notwithstanding the presence of the elastic scaling range at smaller scales. To further understand how actually if intermittency is indeed the same or not as a Newtonian case, what we do is actually compute something called multifractal spectrum. And basically, we measure intermittency not in terms of the velocity, but in terms of the dissipation rate. So when we compute this quantity, the dissipation rate, epsilon, we coarse grain the dissipation rate over a certain scale R, and take the power of it, and then again ensemble, average it. So when we do this, we can expect, let's say, this quantity to grow with R with a certain exponent lambda q. This exponent lambda q, let's say, can be through a Legendre transform. We can actually compute the multifractal spectrum of the dissipation rate, which is what I'm showing here. Now, apart from what this means, the message that I want to give you is that, so these flat symbols are actually experiments done by Menneveau and Srinivastava some years ago for a Newtonian turbulent flow. This black line is our Newtonian simulation. So you can see that we follow quite well the experimental data. The important thing here is to recall, let's say, is that for our polymeric flow at Deborah 1, so the one where the elastic scaling range is maximum, so the one that is mostly altered by the polymers, has exactly, or almost exactly the same multifractal spectrum. That's, let's say, suggesting that yeah, the multifractal spectrum is the same, meaning that the intermittency that you have in the polymeric fluid flow, turbulent flow, at Reynolds number is the same that you would have in a Newtonian fluid. So this is, at least to us, was quite unexpected. Okay, so this leads to the conclusion of the first part. So I will try to accelerate. The second one is shorter. So for more information, you can look at. So this work actually was published. So you can look at it if you are interested. So the second part is similar. So the setup, everything is the same. The only thing that we change is the Reynolds number. So if before we were at very large Reynolds number, now we go at very low Reynolds number. So the work is done in collaboration again with Zal Perlaker and Tuba Ditya Mitra, but also mostly is done by my postdoc Raul Singh. Okay, as I said, we turn our attention to low Reynolds number. So if we have this simple sketch at larger Reynolds number, we see as we vary the Deborah number, so going from top to bottom, we see that the energy spectra varies from the one typical found in turbulent flows. We have an intermediate range of Deborah number in which the elastic scaling range appears. And if we increase the Deborah number even further, we recover the Kolmogorov scaling. So this is what I just explained in the previous part. We know that if we are at a very low elasticity, even zero, if we reduce our Reynolds number substantially, eventually we can end up with a laminar flow. What is known since the experiment by Grossman and Steinberg in the year 2000, what we now know is that even if the Reynolds number is very, very low, if we have polymers dissolved in our fluid and the elasticity of the resulting flow is sufficiently high, it's actually possible to achieve and sustain a turbulent, a chaotic state, okay, with an energy spectra, with a power law energy spectra, which is usually called elastic turbulence. So this topic of elastic turbulence has been studied in the past mostly experimentally. So we haven't actually found a 3D, at least, simulation of elastic turbulence. So we try to do that. So the setup, as I said, is the same as before, and we still have our three periodic box. The difference is that now we are at the low Reynolds number. Before we were 400, now we are around 30. So one order of magnitude smaller than that. So this Reynolds number is sufficiently low that if we simulate the flow of a Newtonian fluid, the fluid becomes laminar. If instead we start increasing the elasticity of the fluid, eventually the flow transition to turbulence. And that's why we have only, I will show you the results only for free Deborah number 1, 3, and 9, because for elasticity below 1, actually we were reverting back to laminar. To further verify that everything that we will see in the following comes only from purely elastic effects and not from, say, small inertial effects, we actually repeated also the simulation by completely removing artificially the nonlinear term in the momentum equation, and indeed we verified that the results were the same. So everything that I will discuss in the next few minutes comes from the non-Newtonian stress term of the momentum equation. So the first result is again the energy spectra. So for the free Deborah number, so the blue curve is Deborah equal 1, then we have green, which is Deborah 3, and the yellow is Deborah 9. So for all the Deborah number, we find a pretty clear power law decay of the energy spectra. And now the energy spectra for this flow is decaying very steeply with an exponent of -4. Interestingly, this exponent is not changing with the Deborah number. Note also that we are making the wave number k non-dimensional with eta, so the Kolmogorov scale. And yeah, but for now, that's it. Once we have the energy spectra, we can actually, in the simulation, we can actually compute also the polymeric energy spectra. This basically is the spectra of the conformation tensor, which also show a power law scaling. So it's less clear than the one of the fluid, but anyway, we found an exponent of around 3.3/2. Now, the interesting thing here is that we can actually obtain the scaling of either the energy spectra or of the polymeric spectra by knowing the other one. Why? Because they are at low Reynolds number, so we can define our turbulent kinetic energy, which is simply the integral of our spectra, and similarly we can define our polymeric energy as let's say the integral of our polymeric spectra. Now, just by the dimensional arguments, just looking at how they scale with the length, we can actually find out that this flow, so the initial terms I said are subdominant, so the only terms that let's say in equilibrium, the terms that remains are only the diffusion term, so the Laplacian of the velocity, and the non-Newtonian stress, so the divergence of the conformation tensor. So we can expect that on equilibrium, on average, these two terms can balance out, and by dimensional arguments, we can just find the relation between the energy, between the polymeric spectra and the energy spectra. So once we know how one of them decays, for example, K-4 for the energy spectra, we can actually obtain how the polymeric spectra decays. And indeed, the numbers work out, because if we have a K to the power -4 stand here, we obtain 3/2. So this is only to say that this scaling comes from a balance between the diffusion term and the momentum, and the nonlinear term, the non-Newtonian stress. Okay, so similar to before, so we have the energy spectra. We can do the equivalent in the real space. So we compute the secondary structure function and found that at small scales it grows with r to the power 2. However, there is an interesting thing here. So if we do the same argument that we did before to connect the energy spectra with the second-order structure function, we may expect that the structure function is actually growing with the power of 3, which instead is not doing because it's growing with the power 2. However, our power 2 is consistent with a simple Taylor expansion, or with knowing or remembering that for any energy, let's say, velocity field with a decay, with a power law decay which is larger than -3, then the second-order structure function always stops and grows as r to the power 2. The reason for that is that this is what even in Newtonian fluid happens at a very small scale, and can be actually derived analytically just doing a Taylor expansion of the definition of X2. So it seems, however, to be a contradiction. So we would expect 3 just by considering the energy spectra, and we found a 2, which is, however, consistent with the Taylor expansion of our S2. So how to reconcile this thing? So the point is, what we found in the Fourier from the Fourier transform is a subdominant contribution of our velocity difference, which comes out only at small r. And to make it, let's say, appear and solve this contradiction, instead of computing the standard second-order structure function, we compute the second difference of the velocity. So now we have the velocity, the difference in velocity between 3 points, a point x, a point plus r, and minus r. If we compute this quantity and plot it, it's shown here, and now indeed we recover our r to the power 3, which is what we would expect by looking at the energy spectrum. So there is really no contradiction, obviously, but the idea here is that we have a subdominant. If we do now a Taylor expansion of our velocity difference, the new exponent is actually subdominant contribution in small r. So if we do the typical second order difference, which is over here, at small r, the term which dominates is the one growing linearly with r, which if we take the power 2 of this will be r2. While what comes from this energy spectra is the Fourier transform of the subdominant contribution, which we can find out by cancelling this term, by looking not at the velocity difference, but at the second difference. So this is similar somehow to what happens in Newtonian turbulence at Reynolds number, because in the limit of, if we do the limit of r going to 0, so as I said, these terms usually dominates at large Reynolds number. If instead we take first the limit of viscosity going to 0, basically we remove the diffusion, the viscous term, and then we repeat this limit. What we found is that our velocity difference grows with r to the power of h1/3, which is actually the Kolmogorov scale, basically, because for the structure function. So if we take the second power of this, we will find 2/3, which is the power for the second structure function. For p equal 3, we would find 1, and so on. So the fact that this exponent is non-integer is what usually makes people call the velocity field to be rough. Now we cannot do this for our elastic turbulence case, because we cannot do the limit of nu going to 0, because we are at a finite and large viscosity, because our Reynolds number is very low. So because of that, our field is not rough but smooth. Usually when the flow field is smooth, would suggest that there is no let's say intermittency, or that there is no, let's say, complications, let's say. But however, elastic turbulence, we can show that there is this subleading term, which is again an integer. And the interesting thing is that coming from this subleading term, we are actually able to find intermittency also in our elastic turbulence flow at very low Reynolds number. To do that, we look at our second difference structure function psi for different orders. We can extract the power of extract the power with which this second difference grows, and we found out that they are a non-monotonic function, similar to what found in Newtonian turbulence at large Reynolds number. For a typical at large Reynolds number, this vertical line should be p/3. Here is larger because it's different, but the important point here is that this is non-monotonic, which means that our flow is actually intermittent. To let's say further prove that, we can look also at the dissipation rate. Right, so we finish. So we can look at our PDF of our dissipation rate. So the fluid one, we can show that it has large tails. So it's non-Gaussian. So this dashed line is a Gaussian distribution. So we can see that we have indeed strong events, but rare, of the dissipation rate. All these, let's say, intermittency actually is in the fluid itself. It doesn't come from the polymeric terms, because if you look at the polymer dissipation term, actually it's a sub-Gaussian. And furthermore, we can again compute the multifractal spectrum to further prove that indeed we have intermittency. These black cross are the same experiment that I was showing in the first part, and the lines are symbols are the one in elastic turbulence. So again, you can see that indeed we have a full multifractal spectrum indicating intermittency. Differently from what we found with the large Reynolds number, here actually intermittency is different from what we would, slightly different from what we would find in the Newtonian fluid. It's not extremely different, but still there are some differences. With this, I conclude. So yeah, the main result, the main conclusion of the second part is that we can actually find elastic turbulence. We can simulate elastic turbulence, first of all. We verify, as it was already known, that it is a smooth field. But this is true only at the leading order. Actually, it has roughness in a subleading term, which actually brings in intermittency into the flow. So this work is currently under review, but it's in archive if you want details. Just to conclude, so we have seen large Reynolds number flow, low Reynolds number flow. So there is a large, let's say, the question that we asked ourselves was how these two connect. So are we able to have a unified view of all the polymeric flows? So we actually varied the Reynolds number going from the large one of before to the small one we just saw, and we can actually see how all these power laws changes, which terms contribute energy balance and so on. And also this is a work under review. So thank you very much for your attention. If you have any questions, try to answer.
So thank you, Marco, for the very interesting talk. So I would say, as you just suggested, we can open the stage for questions. So whoever wants to ask a question, just feel free to unmute your mic and ask your question.
Hello, Marco. This is Christos Vasilikos talking. Hello. Francesco, can you hear me?
Yes, yes.
Yeah. I have two questions for you. From the first one is on your first talk. The second one could be for both. For the first talk, you mentioned this minus 2.3 spectrum, which is interesting, in an elastic range. But you didn't say what the prefactor was. Have you got an idea what the prefactor was? Or might be?
Okay, so you mean, let's say.
So in when the Deborah number is, when there is no polymers, it is epsilon 2/3 to k minus 5/3. You have a prefactor which is a 2/3 exponent of the dissipation.
Yeah.
In this case, where you will have in the elastic range and you have a minus 2.3 wave number spectrum.
Yeah.
Have you checked at all what the prefactor might be?
Okay, so we the point. So if I understand your question, you are asking, let's say, how we can scale it like done by Kolmogorov for the Newtonian case. Different from that case now. So we don't only have epsilon, let's say, and r in u. We also have lambda, so we have an extra time scale. So actually, there are multiple ways in which you can scale your energy spectra. So we tried the one with the in which we were taking into account lambda, which seems to roughly work, but it was not very conclusive. So at the end, we didn't go too much into that. But I'm saying the main point here is that it's not like in the Kolmogorov case where you can, let's say, there is no, let's say, other choice. Here, actually, there are more than one choice that you could do. don't know if that's what was your question.
No, no, you answered my question. I just wanted to know if you have looked at it and whether you have an answer. So I know
There is
now
one
what you
that we tried with, which included the polymer timescale, because as it seems the most obvious. It was roughly working, but of course it was not possible to scale all the different Deborah numbers together. That was not working simply because they have different ranges.
And my second question has to do on the intermittency. For the intermittency, you look at it by looking at higher order structure functions, you know, these exponents and so forth, which in a way perhaps doesn't give much information. Why don't you go back? Why don't you go back to your energy equation? You know, you have the equation d by dt of the energy equals interscale transfer rate minus dissipation and blah blah, and look at how each one of these terms fluctuates. I mean, here you have averages, but when you look at allow them to fluctuate, you will see a picture which is you might see a picture which is very different from what you have on average, and which therefore will force you to explain things differently.
So we tried that at a large Reynolds number. We didn't try that at small Reynolds number. So what we were saying is that pi. So we focus mostly on pi, which is what you also have in the Newtonian case. It was fluctuating in a similar way, let's say, of what you could find in the Newtonian case. That's because the large scales seems, at least in our case, not to be extremely modified by the presence of polymers. So we are injecting the same energy. Pi was fluctuating in the same way as the Newtonian case, which you can also see in terms of the balance here. So at the large scale, okay, the value was different, but still it was everything, most of the energy was transferred by that. So yeah, we were sort of convinced that in this case, intermittency was the same because all the energy was coming from the large scale and then was transferred independently one time by pi and after transferred back by the other by p.
But each one of all the terms here, with perhaps except the very last one, all the terms here would oscillate a lot in time and space.
Yeah.
Well, let's say in time for the time being. Yes.
Yeah. But at different scales, let's say.
So to understand intermittency, you'll have to see how all of them fluctuate, by how much, and whether they correlate when they fluctuate.
Yeah, we didn't try that so quantitatively. We were just looking. We mostly focused on pi f, and that one we didn't see too much difference. But yeah, we know that there is also the Toplium, but we can try that.
Thank you. Thank you very much.
Thank you.
Well, thank you. So let's see if there are other questions from the audience. Once again, just feel free to unmute your mic if you have a question, or and ask the question directly, or you can write in the chat and I can report. And maybe I can ask you a question, Marco. That's in the second part of your talk, where you basically reduced yeah, correct. You reduce the Reynolds number. Exactly, it's on this slide. If I'm not wrong, the theory of Lebedev was pointing out that elastic turbulence should have an exponent of the order of -3, -3.4, and here you show that there is an exponent, an exponential power law like that goes with -4. Do you have an explanation for this discrepancy?
Yeah, their theory actually predicted an exponent, let's say, steeper than 3. So actually, we are not. So 4 in theory is steeper than 3, so it's okay. The main, let's say, difference I would say is that usually in experiments, what people find actually is -3.
Yeah, exactly. Yeah.
-3 is more common, let's say, to be found than -4. In simulation, there are some 2D simulations done by Boffetta some years ago who found -4. Some other simulation done by Watanabe and Goto who also found -4. So in simulations where you have usually at least in these cases of elastic turbulence, you have a quite clear scaling range. It's more common to find something steeper than 3, usually 4 actually. While in experiment, most of the people found 3, but I think in experiment, the scaling range often they are not extremely long. So I don't know if it is a problem of say of extension of the elastic scaling range, or if it is an issue of flow configuration or something.
Yeah, in fact, that was somehow a question actually I want to follow up with, because if I'm not mistaken, like in the simulation of Bofetta, they use Kolmogorov flow, right? And in this case, you are like fully 3D, so it's your forcing term is different. Do you think that it's somehow related to the forcing term? And in the experiments, normally they do have boundaries, so I would expect that boundaries do have an effect on the exponent, right?
So that was my original idea. Actually, recently we did a channel flow of a low Reynolds number, and we found again -4. So I think that I can say that that's not the case anymore. So originally I thought that was the case. So the presence of the wall was somehow changing the scaling range, but it's not. So because I found basically the same scaling also in a elastic turbulence, let's say, channel flow. So it's something else, which I'm not sure. There is a nice paper by Yamani et al., so also Garrett McKinley and others, in a jet, elastic turbulent jet. And they do experiment. And they found actually is a physical regulator from last year, I think. They found again -3. They say that it's universal, at least in their experiment, that exponent. So I don't know if it is a problem of model, it is a problem of configuration, or it is a problem of how the exponent, let's say, is somehow extracted from the experiment or from the simulation. It's somehow obvious, but yeah, so there is this, let's say, mismatch in elastic turbulence spectra between simulation and experiment so far.
Yeah. Okay. So that's thank you. So that was it's actually I don't want to monopolize the the discussion. So let's see if there are other questions. Eventually, I will ask you one more thing on this. Martin, go ahead.
Yeah, hi Marco. Very nice talk indeed. I just have a question off topic. Can you just comment on the numerical scheme? Because people experience to have problems to get this very high Weissenberg number, Deborah numbers. How did you do that?
So yeah, indeed, most of the simulation in the past were done at low Weissenberg number or low Deborah number, exactly because it's not very easy numerically to solve these equations, because the equation of the polymers get unstable. It shows usually the conformation tensor can grow exponentially, so any small perturbation can make it, let's say, explode numerically, and that limited in the past the maximum Weissenberg number or Deborah number that could be reached. So there is a way to fix this problem without. So in the past, they tried to fix this problem by adding to this equation an artificial diffusion term, which could be either, let's say, applied in every point of your domain or only locally when your tensor was growing too fast. So I'm not doing that, because then you have an extra parameter to tune. What I'm doing is you can solve that problem somehow exactly by, instead of solving this equation, you solve the logarithm of this equation. In this case, your exponential growth are no more exponential, and they can be controlled. The drawback of this is that this is the logarithmic of a tensor. So actually, at every point in the domain, every time of your time, let's say, simulation, I need to solve an eigenvalue problem. So it's quite complicated, but it's an exact, let's say, fix to this high Weissenberg number problem. By doing that, then the numerical scheme doesn't suffer anymore from that problem. I didn't invent this method, so actually it's been out for a few years now. The good thing is it's exact. It's an exact solution to that. The problem is that it's computational is very consuming. So as long as you can, let's say, pay the extra computational time, then that solves your problem.
I see. what the base scheme is, that a finite volume scheme, or?
We use a finite difference. So all the terms in our equation are solved by finite difference. Then we, for the Poisson equation, so that we found, because we use a fractional step method to take into account the incompressibility. So the Poisson equation that comes out, we solve it through Fourier. So we decompose in Fourier the Poisson equation. So we are triperiodic, so actually our matrix is diagonal. So it's very simple to do. So everything else is a finite difference, central finite difference.
Is it second order?
Second order, yeah.
Yeah. Many thanks. Yeah.
And in time we use adaptation. Second order.
Okay, thank you. Is there any other participants who would like to ask a question? Just feel free to unmute your mic or to write in the chat, and I can report the question. Okay, that doesn't seem to be the case. Then I can ask you, Marco, once again a question, follow up on the question of Martin. Actually, have you ever experienced the phenomena of numerical stabilization of or stabilization of a numerical instability due to the? I think you used the log conform approach, right? For the have you experienced like phenomena of by changing your scheme that you see artifacts in your numerical solution that are stabilized by this method?
If you mean if I see that it works?
Well, it's sometimes we have some experience in recent simulations that an artifact gets created by the momentum equation, and then it gets stabilized by this approach, because the approach provides an unconditionally stable method to do numerics. So it's not going to blow up because of the extra stress equation, right? So that's kind of provide an extra stabilization to the whole system, which is I don't know if you experience the same.
No, I mean, I don't understand why you should see an artifact on the momentum equation.
Well, if the momentum equation, like if you get, for instance, if you have an advection, if you have a numerically a source of numerical instability in the momentum equation because of the advection term, that can also kind of keep propagating in the solution. That was the
never seen, but experience in
case you don't see this kind of phenomenon. Okay, so that's maybe that's not the case. Okay, so
there are several log conformations.
Yes.
So there are many. So I don't know if we use the same somehow, but the one that I'm using, I mean, I never had had the problem with it since we implemented it.
Okay. So which version of the log conform do you
remember the name? It's in the paper, so I can tell you later.
Okay. Yes. Yeah. Sure. I can refer to it. Okay. Thank you. I see, Stavroula, maybe you can unmute your mic and ask a question. See that.
Hi, thank you very much. Thank you for the wonderful talk, Edoardo. Marco, Edoardo, I don't know which of the two you use. So I have a couple of questions, actually. So in the first part of your talk, you basically studied the contribution of the polymers in a flow that is already turbulent, right? Yeah. So the Reynolds number is defined based on the lambda is 400. What would be the Reynolds number based on the actual geometric characteristics of a flow, let's say channel flow there, just to get an order of magnitude.
So lambda here is the Taylor microscale. So
yeah, it's like a Kolmogorov scale, right?
It's like 10 times the Kolmogorov scale, roughly.
Like 4,000? 4,000, roughly. Okay, so the flow is already turbulent, and then basically by adding polymers, you change the spectra change from the classical like -5/3 to -2/3. Is this universal?
So it doesn't. We try with different kind of models, say, of polymers. So we tried the BIF and a P, and it doesn't change. Yeah. So it
okay, right. So then, when the Deborah number becomes 25, why do you go back to the Newtonian turbulence then?
Okay, that's because so there are. If we look at the so C, the conformation tensor is if you look at the trace of the conformation tensor, it's sort of quantify, let's say, the extension of your polymers. So if you look at the PDF, let's say, of our trace of C as a function of the Deborah number, what you observe is that as the Deborah number increases up to 1, the trace of C was growing as expected, so your polymer are more elastic. The problem is for Deborah larger than 1, the trace of C starts going back to smaller numbers. So it means that polymers are not stretching anymore, or are stretching less than for lower Deborah number. The reason for that is that when the high Deborah number means that the polymer relaxation time is larger. So when the polymer relaxation time is too large, it's not able to, let's say, polymers are not able, they don't get stretched anymore by the flow.
Okay. Yeah, the relaxation time is like higher than the time scale of the flow, so they cannot really stretch within the. Okay.
That's why actually in defining the Deborah number, we use the larger scale of the flow, because for Deborah larger than 1 is when the polymeric time scale is larger than the fluid time scale.
Yeah. Okay. Yeah, that makes sense. Thank you. So in the second part of the talk, you look at elastic turbulence in the absence of inertia, right? So the -4 is for elastic turbulence in when the Reynolds approaches 0.
Yeah, I mean, it's not 0. In our case, it's 30, but it's in a condition in which the Newtonian fluid will be laminar.
Yeah. So, I mean, this like the paper of McKinley actually talks about the universality of the decay exponent, the -3, they claim to be universal, but that's for elastoinertia turbulence.
Yeah.
I mean, in our experiments, we don't find -3 actually. So we were wondering whether you have a comment on this universality, because you find -4 for the
we don't find the 3.
Okay.
So here actually we are varying the Reynolds number. We go from 400 to 40. So 40 is the one from before. So in the middle you have something that you can consider elastoinertia turbulence. As we increase the Reynolds number, we always see 4 at the smallest scale. So actually, let's go back. At the largest Reynolds number, which is this orange, is what I showed before. So we have a Kolmogorov scaling at the largest scale, followed by -2.3, the elastic scaling, right? And then we have a fast decay at smaller scale. The bottom line instead is what I call the elastic turbulence. So we have a very short range of 2.3 at the largest scale, followed by this -4. As we increase Reynolds and we go in between these two, so the -4 remains. It becomes slightly steeper, but it's always there at the smallest scales. So we never find -3. What happens is that, at least for the Deborah one, this 2.3 scaling range expands, and eventually, for sufficiently high Reynolds number, the 5/3 also appears. So the 3 we never find.
Right. Okay. Thank you. Interestingly, we find -2.3 in our experiments, but not -3. Okay. Right. Thank you very much.
So let's see if there are other questions from the audience. Just once again, feel free to unmute your mic or to write in the chat. This doesn't seem to be the case, actually. So, well, I don't see anyone who wrote anything in the chat. Okay, perfect. So I think Marco, thank you once again for the talk. It was very, yeah, it opened up a very interesting discussion, as you could see, in many different directions. So thank you once again for accepting the invitation, and I invite the audience also to thank our speaker of today, and hope to see you soon next week. A good evening, Marco, and a good afternoon to everyone else.